All right, so hello, everybody. Welcome to our fourth session for today. I'd like to, well, sorry, I guess I'll start with my name. My name is Liam Bass. I'm an engineer with Transport Canada's Innovation Center. And yeah, I'd like to call up Dr. Sohrab Sharifi to come and present his piece here. A little bit about him. He is a research associate in civil environmental engineering and earned his doctorate at the University of Alberta. His research integrates advanced techniques into landslide early warning systems, particularly for at-risk railway tracks in Western Canada. Proficient in InSAR, data analysis, and GNSS systems, soft computing, and image processing. He also contributes as a reviewer for esteemed Q1 international journals. Thank you.
Right. Can you hear me? No? How about now? Yep. Right. Thank you for the introduction. Good afternoon, everyone. I know it's not a time of the day usually to hear someone talking about the research, so I try to make it exciting. Well, as exciting as it gets in geotechnical engineering. Anyway, I'm really happy today to be here and talk about one of our recent efforts on making InSAR results more usable and valuable for the railway industry. Infrastructures in Canada, especially railway networks, are at the mercy of ground hazards such as landslides. And considering the vastness of these networks, remote sensing techniques have been a popular tool for monitoring the ground displacements. And one particular example is interferometric synthetic aperture radar, or InSAR. The spaceborne InSAR sensor, it's mounted on a satellite orbiting the Earth, shooting constantly microwaves to the ground and recording the backscatters. Those backscatters can be characterized by amplitudes and phase values as any other waves. The next time the satellite is passing roughly through the same point, it makes the second acquisition. And if you subtract the phase values of these two scenes, a product called an interferogram is generated, which can be later on converted into displacement maps. The interferogram is actually made up of several layers superimposed on top of each other, such as topography, atmosphere, orbital variances, and random noise. And the goal in InSAR analysis is to minimize the effect of these layers and to isolate the contribution of displacements. And once you do that, you just plug in the phase displacement into equation number 2 and get the displacement's actual values. Easy, right? InSAR is a reliable option when it comes to monitoring on a regional scale because of large coverage area and also phenomenal density of targets that it can pick up compared to point-wise instrumentations, in-situ instrumentations that we typically have in geotechnical engineering. Also, it is very good for looking at remote areas, remote places, and is much less susceptible to meteorological phenomena compared to its alternatives that work in the visual range of electromagnetic spectrum. It also has a precision of up to 5 millimeters, which is acceptable for most of applications. But there are also several aspects of InSAR that make you pause when you're considering to use it. First thing is the cost of each scene is something between $1,600 to $2,000 US. And to actually process these scenes, you need special programs, special softwares that are also not cheap. But also the last consideration that you gotta think about it when you're considering using InSAR is that it is only sighted to line of sight. It is only picking up that portion of displacements that when you project that velocity actually along the line of sight. And it has some implications. First of all, you lose an accurate sense of directionality and the magnitude of movements. It also complicates setting the alarm thresholds when you're developing a monitoring system, such as an early warning system, because you can see two regions, both showing very low, same line of sight velocity, but actually one of them could be moving much faster, but simply because of the direction of movements, it wasn't picked up by InSAR. And it's also very counterintuitive to understand and interpret the line of sight velocities. And so decomposing these one-dimensional line of sight velocities into 3D became an interest in academia and also industry. The three components along vertical east-west and south-north axis can be mathematically fused together to make the line of sight velocity using the geometry of acquisition. And because of the relative movement between the Earth and the satellite and a slightly squinted orbit, the satellite sometimes catches a point when it's orbiting toward the north, aka ascending orbit, and sometimes from the north, aka descending orbit. So we actually have two sets of line of sight velocities typically. And equation 3 is actually the system of equation that correlates all of these components and line of sight velocities. But if you look at it carefully, you see it's an ill-posed problem because we have three components, but only two equations. So very, very early on attempts in literature, actually, people started to suggest to ignore one of these components, the south-north component, on the premise of near polar orbit of these satellites. But aside from the fact that by ignoring one of these components, you actually don't make any progresses on getting the directions and the magnitudes of the velocity. But also in my PhD, we realized that sometimes it induces too much error. And so we started looking at other alternatives. We know that there is a bidirectional relationship between landslide processes and ground geometry. So we can leverage this ground geometry and take inspirations from the ground geometry to make compatibility equation between these components so we don't have to ignore anything. The first one that we looked at is the surface parallel flow method, which takes the elevation gradients in east, west, and south-north direction, and in a way that it forces a total velocity to follow the natural terrain. The second one that we looked at is the aspect parallel flow method that establishes the relationship between only horizontal components, east, west, and south-north components of the velocity, so the total velocity follows the slope's aspect angle. To assess the performance of these methods, we started looking at Thompson River Valley, southeastern BC, almost 10 kilometers south of town of Ashcroft. This valley is a very strategic corridor for both CN and CPKC, given that it's like a belt connecting east and west ports. A dozen slow-moving translational landslides traverse both of these tracks in this corridor. And we know that a subhorizontal plastic clay layer accommodates the basal shear surface, and the seasonal changes in the river actually predominantly control the activity level of these landslides. We looked at, particularly for this study, we looked at Ripley, which is one of the most heavily instrumented ones. And luckily, there are 3 GPS devices that we could very accurately compare our results against the direction and the magnitude of velocities that these GPS devices are reporting. So 2 parallels of analysis was done in this study. The first one we call direct analysis. More than 200 scenes archived by European Sentinel-1 and Canadian RadarSat-2 were collected, and we analyzed them using SARPROs. And then we decompose these line of sight velocities using equations 7 and 8, which are modified versions of those systems of equations that I showed you earlier. If you see, when you look at these systems of equations, we have preserved the 3 components, and yet none of these systems are anymore rank deficient. And so since we're decomposing all of these line of sight velocities for each and every single of these pixels, we're able to actually calculate the error in geometry and the magnitude of the velocity vectors that these methods interpret. The second methodological stream in this study is called back projection. So in this way, in this approach, we took the GPS results, we minimized the noise and outliers and everything, and prepared them to be used and processable, and projected velocities on the line of sight of Sentinel-1 and RadarSat-2, and then decompose them back again. Well, while it may sound a little bit futile to do that, but this back projection analysis actually gave us an opportunity to study the impact of these decomposition methods isolated from other sources of error. Saying that, the direct analysis is still pretty much valid, because in the real world application, it's very hard to suppress the impact of these sources. But we use both of them, actually, both of these methods to study the performance of these methods. So this table shows the errors in aspect angle, travel angle, and the magnitude of total velocity vectors as interpreted by SPFM and APFM at the location of GPS units. And before I get to the results, I should add that these are the average errors, because very limited variations were observed between GPS locations of GPS units. First observation is that the SPFM's aspect angle and back projection has a very large error, as much as 20 degrees, and it even grows to 36 degrees in direct analysis. The second thing is that in travel angle, as interpreted by APFM, in direct analysis, we also see a very large error, as much as 14 degrees. But other geometrical errors are within an acceptable range. So kind of to sum up, we see that these decomposed velocities might be geometrically altered. How about the errors in the magnitudes of the velocities? As you see, as interpreted by SPFM, both in back projection and direct analysis, the errors are large, but without any meaningful differences between back projection and direct analysis. And also, the same is true for APFM and direct analysis. So if you look at these errors, both in geometrical parameters and the total magnitude, the magnitude of total velocity, we'll see it's like that SPFM is rotating vectors, just rotating them without touching the magnitudes of velocity. And APFM is kind of overestimating the vertical component that makes the error in travel angle larger and larger, and also makes the error in total, the magnitude of total velocity larger. When we started looking at the Ripley in its entirety, we also started to see the patterns again. You can see that in both subfigures A and C, that SPFM is rotating vectors toward north for all of these targets. And the same goes also for the travel angle. For APFM, you can see that in subfigure D, that these vectors are kind of oversteepened. So at this point, we were convinced that it's no coincidence that these methods are acting like this. There must be more to it. So if you remember, SPFM main assumption was something like this. If we rearrange terms and write them in a derivative form to describe the error between these components along south-north component, vertical, and east-west, you'll see that these ratios, which are 1 over IN, that is the elevation gradient along the south-north direction, and I over AN pop up, and these parameters vary between 5 to 10 and 2 to 4. And so even a minuscule error in one of these factors can be magnified up to 6 times in south-north component. So it would justify why all of these vectors are rotated toward north. Okay, so that would justify the direct analysis errors that we were seeing, but what about the back projection? Because there were no errors in the back projection. So if you sit down and very patiently solve those equations manually and calculate the aspect angle as the SPFM interprets, you will see those ratios pop up again. So the same argument is still valid, and that shows that this method is very sensitive, and no matter what, it will bias the vectors towards south-north direction. How about the steeper travel angle as interpreted by APFM? So it is very important to remember that the images that we use had different resolutions. One of them had 20 by 5, and the other one had 3 by 3. And so we had to lower the reliability threshold for Sentinel-1 to get a comparable density of points between these two displacement maps from these two satellites. And so that means that one of them had a lower accuracy. And if you account for that, and if you substitute the ratios of errors between these two satellites in those equations and do the calculations, you will see something like this that shows, for example, a unit weight of error along the line of sight velocities interpreted by radar SAT-2. These are the portion of errors received by each of these components. So you'll see that the error in vertical component is almost 4.6 and 8 times larger than the other components. So again, it would justify why the vectors were oversteepened and the travel angle was kind of overestimated. So in conclusion, error in line of sight estimations are manifested with geometric alterations in these methods. So it is not possible to use and pick one of these methods and use them as a standalone method to decompose line of sight velocities. And rather, you gotta have a hybrid approach and use SPFM for magnitude and travel angle, while you use APFM for interpreting the travel angle. At the end, I'd like to acknowledge the role of our supporters and collaborators in Railway Ground Hazard Research Program. RG-Sharifi, the unique nationwide collaboration between industry, academia, and government to devise smart solutions for challenges that the railway system faces in Canada. Thank you very much. I'd like to hear your questions.
All right, so we have a minute or two for questions. Is anybody questions?
Like a good thing or bad thing?
Thanks so much for your interesting research. My question is about so these InSAR, and so have you considered also the overlap of like the other orbital satellites that can like cover some of the portions that are covering and the space side of survey and like those accumulated data can correlate increasing the accuracy or verification between the two different satellites?
Well, yes, but the problem is that the data, the free available data for InSAR is very, very limited. So pretty much your hands tied up with Sentinel-1. And oftentimes, if you're lucky, you just get one set of ascending and descending, except for the times that it's right coincidentally on the overlap of two ascending orbits. But the problem is that if you want to use them and have a, how do you say it, redundant observation, sort of, because of the parallelity of the aspect angle between two satellites having the same orbit, you will have a singularity in the equations that we'll use. And so it's kind of, it becomes useless some sort of. And they become the same actually when you're solving the equations. So the other thing you can do is that to use that redundancy and incorporates other statistical methods such as least squares method or regularization or any other sort of method like that. You can use those to minimize the error, but none of them actually will solve the problem, the ill-posed problem that you have for decomposing line of sight velocities. We actually did that, and Nemo actually was smart enough to put up the title of his paper. We published it in Landslide Journal. We compared all different sorts of combinations between these satellites, and we sort of concluded that redundancy is not good. Because oftentimes, if you just want to add more, toss in more Sentinel-1 images in the analysis, again, because you're having a very coarse resolution, you're losing accuracy. And if you want to pay for radar SAT-2 images or other satellites, if you're lucky enough, you barely just have enough funds to pay for one set of orbits. It's because these sort of things are very expensive. Thank you. Thank you.
Any other questions? I'm seeing none. Okay, thank you.
Thank you so much.
Thank you.